In the series Advanced Mathematics, we are going to start lecture 9 of chapter Vector Calculus, and in this lecture we will talk about the Gauss Divergence theorem. So we start this lecture with the statement of Gauss Divergence theorem. We are saying E be a closed and bounded region in three-dimensional space whose boundary is a closed surface S. Now it is important over here, the surface now we have it is a closed surface. When we were talking about the Stokes theorem, it was an open surface. Now we are saying it is a closed surface, and f vector be a vector point function which is continuous and has continuous first partial derivatives in a domain that contains E. Then we have the double integral, we are talking about the surface integral of f vector. We are saying that is equal to the triple integral or the volume integral, we are saying, of divergence of f vector into dv, where this E is this E we are saying it is the closed and bounded region by this surface S. Now we are saying the surface is closed. So suppose we are talking about a sphere. So this is the surface of the sphere, and this volume is basically the volume of this sphere, the surface, the volume enclosed by this surface we are saying. So to prove this result, we are writing f vector is equal to f1 I cap plus f2 j cap plus f3 k cap. Then f dot ds vector, we are saying f vector dot n cap into ds. So we obtain this is equal to f1 n cap dot I cap into ds, and likewise we have to add all these three terms. We are obtaining the terms in this form. Then we are having divergence of f vector. We are talking about this value, divergence of f vector. We have it is curly f1 by curly x plus curly f2 by curly y plus curly f3 by curly z. So if we substitute these values over here, so what we have to prove is, we have to prove that this integral, these surface integrals, this is the value of this whole integral, that is equal to the volume integral of these three terms, sum of the volume integral of these three terms. So we are saying what we have to prove, what we are going to prove now is that this double integral of f1 into n cap dot I cap ds, it is equal to triple integral of curly f1 by curly x into dv. Similarly, we have to prove this second result and we have to prove this third result. So we start the proof of this third result, the last one, and we will prove this result, and similarly on the same lines we can prove the first two. So we assume that the surface that is given to us, suppose we are talking about this is some closed surface that we have, and it consists of the boundary, this top surface we are saying it is S1, this bottom surface we are saying it is S2, and this vertical surface that we have, this surface we are saying, this surface we are saying it is S3. Now this top surface we are saying, this S1 we are saying it is some z is equal to g of x comma y. This bottom surface we are saying this is z is equal to some h of x comma y, and this surface S3 we are saying it has the value of z that is bounded between h and g of x y. So if we consider the projection of this surface, we are talking about the xyz plane. We have this is the xyz plane over here, and we are talking about the projection of this surface on the xy plane. This is the projection we are getting over here. We are saying the projection we have, it is in this form. This is the projection of this surface in the xy plane. Then if we calculate the triple integral over E, curly f3 by curly z dv, we can write this is equal to double integral over r. This is the region r we have, and the limits of this z we are substituting over here. we have, it is the limits of z we have, they are varying from, it is from h of xy to g of xy, and the function we have, it is curly f3 by curly z into dz, and over here we have, it is dx into dy. So on solving this, what we obtain is, this is double integral over r, we have f3 xy g of xy minus f3 xy h of xy, and then we have, it is dx into dy. Now if we calculate the values of the double integrals, the first we have is, it is double integration over s1 f3 n cap dot k cap into ds. Now when we are talking about this n cap dot k cap, we are saying this is equal to double integration over r, this region r we are saying, the projection we are talking about, and it is f3 of xy g of xy. Then we have, in place of ds, this is n cap dot k cap into ds, it is dx into dy. Similarly, on the surface S2, we are having this value as the, with the negative sign, and on S3, this term is equal to 0, because when we are talking about the surface S3, if I plot the normal over here, we are having, this is the direction of normal, this is the direction of k cap, both are perpendicular to each other, so we are saying that n cap dot k cap is equal to 0, so we are getting the answer as 0. In this case, we have n cap dot ds, over here the value of n cap is in the direction of z, in over here this is in the opposite direction of z, so we are saying n cap dot k cap, that is equal to minus 1, so we are writing the value in this form. So from both these results, look at this value. Now the total value you will obtain, it is sum of these three values. So what we obtain from this is that triple integration f vector, that is f3 n cap dot k cap into ds, that is equal to the double integral of difference of these two terms into dx dy. Now similarly, we can prove, this is the third part we have proved. Similarly, by considering the surfaces, different surfaces, we can prove the result that for f2, and we can prove the result for f1. And finally, by adding all these values, we will obtain the required result. Now next we have is, if the position vector of a point xyz within a closed surface S, we are saying we have a closed surface over here, and this is the point xyz that we have, this is xyz, and this is the position vector corresponding to the origin. So there are two cases, either the origin, it can be inside this, or the origin can be outside this surface, and this vector, it is given to be this vector. In both these cases, it will be given by r vector. We have to prove that the double integral over s, r vector over r cube n cap dot ds is equal to this value for these two cases, when O lies inside outside the S and O lies inside the S. So first case we are considering, if O lies outside the surface S, the O lies over here, then this function r vector over r cube is continuously differentiable at every point of S, and if we calculate the divergence of r vector by r cube, you know the value, it is sigma I cap curly by curly x into r vector by r cube. This is equal to sigma I cap dot I cap by r cube minus 3 by 4 r vector curly r by curly x, it is x by r. So if we add these values, I dot I, this will be 1 plus 1 plus 1 3 by r cube, minus the next value we will have, it is 3 by, it is over here it is r raised to the power 4 So the value we will obtain it is r raised to the power 5 into r square. So the answer we obtain it is 0. So we are saying the triple integral over V divergence of r vector over r cube into dv is equal to 0. So by Gauss divergence theorem, we are saying that this value, this is 0 when O lies outside the surface S. Now next we consider the case when O lies inside S. So we are saying this is the surface S that we have, and the point O, the origin we are saying, suppose it is at this point O, and it is being given that if we are considering any point over here, it is x, y, z. This is the position vector we have, it is r vector. Now if this point O it lies inside this surface S, then we cannot apply the Gauss divergence theorem in this case. So what we are going to do over here is, we are going to consider another small sphere whose radius is epsilon about this point O, and we are naming this a surface as S dash. Now if we look at the region between S dash and S, we are talking about this portion, and we evaluate this integral in this region, we are getting double integration over S r vector over r cube dot n cap into ds plus double integral over S dash r vector over r cube dot n cap into ds. This is equal to triple integral over V divergence of r vector over r cube into dv, where this region S dash we are saying this is the portion which is this. Now this volume we are talking about, this is the volume between these two regions. This is the volume between these two regions. So for this volume we are saying this origin it lies inside this portion. So it lies, this origin it lies outside this volume. So value of divergence of r vector over r cube, it is 0 over here. So what we obtain from this is that double integration over S r vector over r cube dot n cap into ds plus double integral over S dash r vector over r cube dot n cap into ds. This value is equal to 0. Now we are talking about this portion S dash. We are talking about this portion S dash. We are saying this S dash, we are saying this is the origin O. This is a sphere. So from this origin O, if we draw any vector over here, that will be the normal vector for this surface. It is a sphere, so this will be normal vector for this surface. So we are saying the value of n cap we have, that is minus r vector over mod of r. So this is equal to minus r vector over epsilon. We have taken the radius of this sphere to be epsilon. So what we obtain is that r vector over r cube dot n cap, that is equal to minus epsilon square over epsilon raised to the power 4, that is minus 1 by epsilon square. So what we get from this is, now we come back to this integral, we are writing it is double integral S dash r vector over r cube dot n cap into ds, that is equal to minus 1 by epsilon square double integral ds of this surface S dash. So this is equal to minus 1 by epsilon square 4 pi epsilon square. So we are getting the final answer as minus 4 pi. So this is the value of this integral. So we obtain from this result, we obtain the double integral over S r vector over r cube dot n cap ds, that is equal to 4 pi. And hence we obtain that whenever this point O it lies inside this volume, then the answer we have it is 4 pi, and when it lies outside this volume, the answer we have it is 0. Now next we have is evaluate double integral r vector dot n cap into ds, where r is, this S is a closed surface. So we are using the divergence theorem. We are writing it is r vector dot n cap into ds, that will be equal to triple integral of divergence of r vector into dv. Now divergence of r vector means we are saying it is del y del x into x plus del y into y plus del y del z into z. So answer we obtain, the sum of all these values, it is 3. So we are getting it is 3 times triple integration of dv. So it is 3 times v, where v is the volume enclosed by this closed surface S. Yes, v is the volume enclosed by the closed surface S. Next we have is, if S is any closed surface, we have to prove that the double integral curl of f vector dot ds is equal to 0. Then by the Gauss divergence theorem, we want to evaluate this term. We are writing this is equal to triple integral over the volume V. Volume V is the volume enclosed by this surface, and we are saying it is divergence of curl of f vector into dv. And we know that the divergence of curl of f vector, it is equal to 0. So we are saying this value comes out to be equal to 0. Next we have is, if f vector is always normal vector to a given surface S, we have to show that the value of triple integral of curl of f vector dv is equal to 0. Now let us suppose that a vector be any constant vector. Then we have triple integral over v divergence of f vector cross a vector into dv. We can write this is equal to triple integral over v, it is del vector cross f vector dot a vector into dv. We are saying this is just like the triple product, it is del vector dot f vector cross a vector, and this value is equal to this, and this is equal to triple integral of curl of f vector dot a vector into dv. Now look at this term over here. We are saying double integral f vector dot a vector dot n cap into ds, that is equal to double integral over S, this is over the surface S, it is n vector cross f vector dot a vector into ds. Now it is being given over here that f vector is always normal to the given surface S. It means it is given that n vector normal to the surface cross f vector is equal to 0. So from this result, we are saying n cross f vector is equal to 0. So this implies us that this integral is equal to 0. Now by the Gauss divergence theorem, we can write this integral, this is equal to triple integral over v divergence of f vector cross a vector into dv, and we have proved that this value, this is equal to curl of f vector dot a vector into dv. So combining both these results, we are saying combining these three results, we obtain that triple integral over v curl of f vector dot a vector into dv is equal to 0. Now since a vector is a constant vector, so this implies us that triple integral over v curl of f vector into dv is equal to 0, and this is what we have to prove. Now next we have is this f vector, it is given to us. We have to find the value of double integral of f vector dot n cap ds over the closed surface bounded by the plane z is equal to 0, z is equal to 1, and this is the cylinder given to us. So we use the Gauss divergence theorem to evaluate this value. We are saying this is equal to triple integral over v divergence of f vector into dv, where v is the volume enclosed by this cylinder. Now if we calculate the divergence of f vector, the value we have, it is curly by curly x, it is 1, then it is minus 1, then it is plus 2 z. So we get it is equal to 2 times z. So what we have to evaluate is, we have to evaluate the triple integral over the volume V. It is 2z dx dy dz, where this volume V, it is the cylinder, x square plus y square is equal to a square, z is equal to 0, z is equal to 1. Now if we convert this to the polar form, we obtain this equation of this circle. It can be written in the form x is equal to r cos theta, y is equal to r sin theta. We are writing z is equal to z. So this integration will become triple integral. It is 2z r dz dr d theta. The value of z, it is varying from 0 to 1. The radius of this circle, it is varying from 0 to a, and it is complete circle. So we are saying the value of theta, it will vary from 0 to 2 pi. So we are writing this is equal to integration 0 to 2 pi d theta, then integration 0 to a r dr, then 2 comes out of this bracket, it is z dz, and limit for z we have, it is 0 to 1. On solving this, we will obtain this is 2 into 2 pi into this is r square by 2. So we get it is a square by 2 into 1 by 2. So this value comes out to be a square pi. So by Gauss divergence theorem, we are saying the value of this integral is equal to a square pi. Next is find double integral f vector dot n cap into ds, where this f vector is given over here. This is the value of f vector, and s is the surface of the sphere having the center this and radius 3. So again we are using the Gauss divergence theorem. We are saying this integral, this is equal to triple integral over v. V is the surface or the volume enclosed by the surface of the sphere. It is divergence of f vector into dv. So divergence of f vector, if we calculate in this case, we get it is 2, then it is minus 1, then it is plus 2. So this is equal to 3. We are talking about partial derivative of with respect to x, partial derivative with respect to y, partial derivative with respect to z. So this value becomes triple integral 3 times dv. dv is the volume enclosed by this sphere. Now the radius of the sphere, it is given to be 3 units. So we are getting this is equal to 3 times the volume of this sphere. So it is 4 by 3 pi r cube, and this value comes out to be 108 times pi, and this is the value of this integral. Next is use divergence theorem to evaluate the value of this double integration v vector dot ds vector, where v vector is given in this way, and s is the boundary of the region bounded by the paraboloid this, it is z is equal to x square plus y square, and the plane z is equal to 4y. So to evaluate this integral, we are using the Gauss divergence theorem. We are saying the value will be equal to triple integral over v. It is divergence of v into dv. Now divergence of v, if we calculate, we are talking about this function is given, divergence of v, that will be 2xz plus 1, then it is minus 2xz. These two values gets cancelled and we are left with this 1. So what we are calculating over here, we are saying this is equivalent to triple integration over v, and this whole value, this is the volume bounded by the paraboloid z is equal to x square plus y square, and plane z is equal to 4y. Now if we use the cylindrical coordinates over here, we are substituting x is equal to r cos theta, y is equal to r sin theta, and z is equal to z. We are saying this equation, this will transform to the form z is equal to, this value will become r square. So we are saying that the value of z, that is varying from r square up to the point 4y. We are saying z is varying from r square to the point r square sin theta. It is 4 over here, so it is 4 r square sin theta. and the projection of this, when we are calculating this integral, we are saying the projection of this on the xy plane, that will be a circle. The projection of this paraboloid in the xy plane, that will be a circle, and the equation of this circle that will be given by r is equal to 4 sine theta. The equation of this circle, it is r is equal to 4 sine theta, because we are taking the projection using this equation. It is z is equal to 4y. When you substitute it over here, you will obtain the equation is x square plus y square is equal to 4y. When you make this substitution, x is equal to r cos theta and y is equal to r sin theta, you will obtain that the value of r, you will obtain it is 0, or r is equal to 4 sin theta. So this is the equation of this circle. So we are saying the value of the volume that we will have, it is triple integral over v. Then we have changed it to spherical cylindrical coordinates. So we have r dr d theta and dz. The function we have, it is 1 over here. So we can write this is equal to triple integral, it is r dz dr d theta. Z is varying from r square to 4r sin theta. Then r is varying from 0 to sin theta. It is 4 sin theta over here. And the value of theta, it is a complete circle, so it will vary from at this point the angle we have 0, and then this is a complete circle, then up to this the angle we have, it is pi. So it is varying from 0 to pi. So we have to evaluate this integral. So on solving this, we obtain that is integration 0 to pi 4 by 3 r cube sin theta minus r raised to the power 4 by 4. Limits for r we have, it is r is equal to 0 to r is equal to 4 sin theta. And this integral is equal to integration 0 to pi 256 by 3 sin raised to the power 4 theta minus 64 sin raised to the power 4 theta into d theta. This is equal to, when we use the reduction formula, we obtain this value is equal to, it is 64 by 3 integration 0 to pi sin 4 theta d theta. And if we make this half angle, we obtain it as pi by 2, and this value it will be multiplied with the 2. And by using the reduction formula, the value of this integral we have, it is 3 into 1 into 4 by 2 into pi by 2. So the answer we obtain, that is equal to 8 pi. So this is the value of this integral, of the required integral. Next is verify the divergence theorem. This A vector is given, taken over the region in the first octant bounded by the cylinder y square plus z square is equal to 9 and the plane x is equal to 2. Now the value of A vector, it is given, it is 2x square y I cap minus y square j cap plus 4x z square k cap. And we are talking about the first octant bounded by the cylinder y square plus z square. So in the first octant, the cylinder will look something like this. This is the boundary of the cylinder and it is bounded by the planes on all other sides. So we are saying that S1 is the rectangular face on the xy plane. This is S1 plane. This plane we are saying, this is S1 plane. Then S2 will be on the xz plane. This plane we are saying, this is the S2. Next we have S3 is the octant in the YZ plane. We are talking about the YZ plane, means we are talking about it is OBC, that is the plane from this side, it is S3, and a plane from this front side, it is S4, and this region, this is S5, this curved region we are saying. So if we calculate the value of this integral, we have to verify the Gauss divergence theorem. So we are calculating the value of double integral A vector dot n cap into ds on the surface S1, on the surface S2, S3 and S4. Now when we are talking about the surface S1, if we plot the normal to this surface, it will be, the normal will be in this direction, that will be minus k cap. Normal for this surface S2, that will be in this direction, that will be minus j cap. Normal to this surface S3, that will be in this direction, that will be minus I cap. And normal to this surface S4, that will be in this direction, that will be I cap. And normal to this surface S5, that will be given by n cap, that is equal to the derivative of this function, it is we are getting it is 2y I cap j cap plus 2z k cap divided by square root of 4y square plus 4z square. And this value, this 2 gets cancelled over here, and square root of y square plus z square we have it is 3. So we are writing this value, we have it is 1 by 3 y times j cap plus z times k cap. Now we want to evaluate these integrals. Now if we take the dot product, we are talking about the surface S1, we are talking about S1. So n cap dot on the surface K1 we it is minus k cap. So we are saying in place of n cap we have it is minus k cap, and we are taking dot product over here. So what we are left with is 4xz square with the negative sign, and on this surface we are saying this is the xy plane, the value of z we have it is 0. So this whole value a cap dot n cap on this surface it is 0. So integral on S1 it comes out to be 0. Next we are saying integral on S2. When we are talking about S2, S2 is this surface we are talking about. On S2 we have it is minus j cap, and the value of y we have it is 0. So we are saying the answer in this case it is 0. On S3 we have x is equal to 0. On S3 we have x is equal to 0, so answer is 0. On S4, when we are talking about this surface S4, the normal vector we have it is I cap. The normal vector we have it is I cap. So a vector dot n cap, that will be equal to 2x square y, and the value of x at this point it is 2. So we are writing it is, this value we are getting it is 8 times y. So we get it is double integral over S4 8 times y dy dz. Now if we take the projection on the yz plane, we are saying that we are having, this is the portion of the circle we are having, and the equation of this circle it is this S4 we are saying, when we take the projection it is basically we are saying it is y square plus z square is equal to 9. So if we change it to the polar coordinates, we obtain this is double integration 8, then it is y, in place of y we are writing it is r cos theta, then it is r dr d theta. The radius vector it is varying from 0 to 3, and theta it is varying from 0 to pi by 2. So if we solve this, we are getting it is 0 to pi by 2. We have the value it is cos theta d theta, 8 comes out, then it is integration 0 to 3 r square dr. Now we integrate this value. Now when we integrate this value, the answer we obtain it is equal to 72. It is dr over here. Now similarly for the surface S5, we are talking about this surface, we have obtained that n cap is equal to 1 by 3. Then it is, the value we have it is y j cap plus z k cap. Now if we calculate the value of a vector dot n cap, the answer we have it is 1 by 3 into minus y cube plus 4xz cube, and the value of ds, if we take the projection, we are having over here x, y and z, all three variables are there. So we are writing them, this equation of the circle in the parametric form. We are writing y is equal to 3 cos theta, z is equal to 3 sin theta. So the equation, the value of ds we will obtain, that will be 3 d theta dx. So the integral we will obtain, it is double integral over S5 a vector dot n cap into ds, that is equal to, when you substitute these values over here, you will obtain it is double integral minus 27 cos cube theta plus 108 x sin cube theta then we have it is dx d theta. The limits we have it is 0 to 2 and 0 to pi by 2. Now on solving this integral, the calculation these are shown over here. On solving this integral, the answer you will obtain it is 108. So the net value we obtain by adding these values, we are saying we have added all these 5 integrals, and the total value we obtain that is 72 plus 108, and the answer comes out to be equal to 180. Now next we have to evaluate the value of divergence of this integral. It is triple integral of divergence of A into V. So if we calculate the value of divergence of A, I think divergence of A we have calculated, the answer you will obtain it is 4xy minus 2y plus 8xz. So our integral becomes, we are talking about it is triple integral 4xy minus 2y plus 8xz into dx dy dz over the volume V bounded between this cylindrical portion. Now if we substitute over here, y is equal to r cos theta, z is equal to r sin theta, and x is equal to x. Then this integral it changes to the form, it is triple integral, then it is 4xr cos theta minus 2r cos theta plus 8xr sin theta into r dx dr d theta. The limits for r, the radius vector over here, it is varying from 0 to 2. Then this is the variation of x. The x is varying from 0 to 2. At this point we have it is 2 0 0. X is varying from 0 to 2. The radius vector it is varying from 0 to 3. And this is the circle in the first octant. If you take the projection in the yz plane, so we have it is 0 to pi by 2. Now if we integrate this equation, calculations these are shown over here, we are talking about this integration. Now if you integrate these values, you will obtain the answer is 180. And this is what we have to prove, that in both the cases the answer is 180. So we are saying both the integral they are equal. So we are saying that the Gauss divergence theorem is verified in this case. Next is verify the Gauss divergence theorem for f vector. This is the f vector given, taken over the rectangular parallelopiped. These are the planes given. It is 0 is less than equal to x is less than equal to a, 0 is less than equal to y is less than equal to b, and similarly this last plane. So clearly this is a closed surface. I think this is a closed surface. And if we plot all these points, we will obtain something like this. We have this figure, and we have named all these planes. This plane we are saying this is S1. The normal vector to this it will be minus k cap. Then we have the plane that is z is equal to c. We are talking about this plane. The normal vector that we will have it is k cap. We are saying this is the plane S2. Then we have the zx plane. We are talking about this plane. The normal vector we have it is minus j cap. This is plane S3. Then we have this plane, this is j cap. We are saying this is the plane S4. Then we have the plane over here that will have, we are saying it is the yz plane. The normal vector will be minus of I cap. This is the plane S5, and this front plane we have it is I cap, and this is the plane we are saying it is S6. Now we are talking about on S1. We are saying this is the plane S1. We are saying we have the value it is minus k cap, and the value of z we have it is 0. So if you will look at this value, you will obtain that n cap into f cap, you will obtain that is equal to x into y. When we are talking about S2, we have k cap over here. You take the dot product over here. You will obtain the value of, this is on S2 we are writing f vector dot n cap, that will be equal to, again it is xy, and the value of z it is c. So we are writing it is c square minus x into y. Now if we evaluate the integral, we are talking about the double integral over S1 f vector dot n cap into ds plus double integral over S2 f vector dot n cap into ds. We are saying the value we obtain by adding both these, it is in place of this value we are writing it is xy, in place of this value we have it is c square minus xy. So we are getting c square double integral over S2, it is ds, and ds is, this is S2 you can write or S1 you can write, it's up to you that how you want to write this value. Both these limits, these are same because we are talking about the area over here. The limits that are same, we are writing both these values, these are equal to S. So we are writing this value, you will obtain it is c square double integration ds, and the area it is 0 to b and 0 to a, that is a into b. So we are getting a b c square. So this is the value of sum of these two integrals. Similarly, when we are talking about the sum of the integral corresponding to the phase S3, S4, S5 and S6, we are getting the answers in this form, and by adding all these values we obtain that the integral of double integral of f vector dot n cap into ds, that is equal to sum of all these three values, and the answer comes out to be equal to ABC into A plus B plus C. Next, to verify the divergence theorem, we are calculating the value of triple integral over of divergence of f vector into dv over the volume V. Now, if we calculate the value of divergence of f vector, the answer we have it is 2x plus 2y plus 2z. So we are evaluating the value over here, it is triple integral 2x plus 2y plus 2z into dz, dy, dx. Limits they are varying from 0 to c, 0 to b and 0 to a. And on solving this integral, again the answer we obtain it is a b c into a plus b plus c, and clearly both these values, these are equal to each other. So we are saying that the Gauss divergence theorem it is verified. Now the next question we have is verify divergence theorem for the vector field. This is f vector given, taken over the region bounded by the cylinder x square plus y square is equal to 4, z is equal to 0 and z is equal to 3. So if we talk about this cylinder, we are saying it is, this is the cylinder we have, and it is bounded by z is equal to 0 and z is equal to 3. So this is the plane we have, z is equal to 0, this is the plane z is equal to 3, and this cylinder equation it is x square plus y square is equal to 4. Now if we plot the normal vectors corresponding to this surface S1, this is S2, and this surface it is S3. The normal it is minus k cap, normal over here it is k cap, and normal corresponding to it is 2x I cap plus 2y j cap divided by 2 square root of x square plus y square, and this value it is 2. So we are having it is 1 by 2 into x I cap plus y j cap. This is the normal vector corresponding to this surface S3. Now next we have to calculate is the value of, on S1 we are saying, we are calculating first the value on S1, the value of f vector dot n cap, and we have z is equal to 0. So the value we have it is minus k cap, this value when we substitute, the answer we obtain it is 0. On S2 we have f vector dot n cap, we are talking about this is, we are taking the dot product with k cap again, and the value of z it is 3. So the answer we obtain it is f vector dot this is equal to 9. So when we calculate the integral, we are saying integration 9 times ds, and we are talking about surface S2. Surface S2, it is a cylinder of radius 2. So, the answer we are getting over here, it is 9 pi into 2 square. We get it is 36 times pi. Next, we are talking about the region S3. Now, on S3 we are saying F dot n cap, that is equal to, we have 1 by 2 over there. Then we have x I cap plus y j cap. We get it is 4x square I cap. Then it is minus 4y cube. It is not 4, it is 2y cube. So, we have both the terms of x and y, then we have z over there. So, when we are calculating the integral, we are saying it is double integral 1 by 2. The equation of the circle we have, it is x square plus y square is equal to 4. So, we can substitute x is equal to 2 cos theta, y is equal to 2 sin theta. So, this equation will become, it is 1 by 2, then f dot dn, this value will become, it is 16 cos square theta minus 16 sin cube theta. Then the values we will have, it is 2 d theta dz. Now, this 2 and 1 by 2 gets cancelled. So, the integral we are left is, we have taken 16, this is 16 cos cube theta minus 16 this, and the limits that we have, it is, the limits for z they are varying from 0 to 3, and the limits for theta they are varying from 0 to 2 pi. And on solving this integral, we have solved this integral, the value we obtain, it is 48 times pi. So, we are saying the total value of the integral, the double integral over S, f vector dot n cap into ds, the total value we will have, that is equal to 36 pi plus 48 pi, that is equal to 84 pi. This is the value of total integral, double integral f vector dot n cap into ds. Next, we are calculating the value of triple integral divergence of f vector into dv over the volume V. Volume V is the portion of the cylinder we are saying. So, if we calculate divergence of f, we get it is 4 minus 4y plus 2z. We are saying we have triple integration over there, and then we have the derivative, it is dx, dy and dz over the volume V. Now, if we change it to the cylindrical coordinates, we are substituting x is equal to r cos theta, y is equal to r sin theta. This integral will become, it is triple integral 4 minus 4r sin theta plus 2z. Then we have dz, dr and d theta. The limits for z they are varying from 0 to 3. Limits for r, the circle that we have, its radius is 2. So, limits for r they are varying from 0 to 2, and theta, it is a complete circle. So, it is varying from 0 to 2 pi. So, if we separate these terms, we obtain this integral in this form. We have obtained the integral in this form. And on solving this integration, the calculation these are shown over here, that you can try at your own. On solving this integration, you will obtain the answer as 84 pi. So, we are saying by comparing both these values, this is 84 pi, this is 84 pi. We are saying the value of the integral divergence of f vector into dv, that is equal to the value of the integral f vector dot n cap into ds. Next is use the divergence theorem to evaluate the surface integral f vector dot ds vector, where f vector is given and s is the surface of the sphere, x square plus y square plus z square is equal to a square. So, by using the divergence theorem, we are saying this value is equal to triple integral divergence of f vector into dv over the surface over the volume bounded by this sphere. Now, if we calculate the value of divergence of f vector, the answer we obtain, it is triple integral, it is 3x square plus 3y square plus 3z square into dx dy dz over the volume V. V is the volume bounded by the sphere. So we are writing this is equal to triple integration 3 x square plus y square plus z square into dx dy dz over the sphere V. Now we use the spherical polar coordinates. We are writing x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. The integral will become, it is 3 times triple integral r square, in place of x square plus y square plus z square we will have r square. Then we will have r sine theta dr d theta d phi. Now the limits for r, they are varying from 0 to a. The limits for theta, they are varying from 0 to pi, and limits for phi, they vary from 0 to 2 pi. This thing we know from the spherical polar coordinates. So on solving this, we will obtain it is 6 pi. 6 pi we will obtain corresponding to this integral corresponding to phi, we will have it is 2 pi, we will get 6 pi. Then it is integration 0 to pi sine theta d theta, then integration 0 to a r is to the power 4 dr, and on solving this the answer we obtain it is 12 by 5 pi a raised to the power 5. These calculations, these are shown over here. So we are saying that the value of this integral, integration f dot ds over the surface S, the answer we have it is 12 pi a raised to the power 5 divided by 5. Next is use divergence theorem to evaluate this integral, where S is the portion of the plane x plus 2y plus 3z is equal to 6. So if we plot this plane, it will be of this shape. We will obtain the figure in this shape. Now this, from this integration we can write the value of f vector that we have, that is equal to x I cap plus y j cap plus z k cap. So divergence of f vector we have, that is equal to 1 plus 1 plus 1, that is equal to 3. So if we have to calculate the value of double integral f vector dot ds vector, we are saying ds vector is basically dy dz, then dz dx, then dx dy. We are saying the value we have, it is equal to triple integral over v, it is divergence of v into dv. So we are writing this value is equal to triple integral, it is 3 times dv over v. Now we are talking about the volume bounded by this figure. We are saying we have this plane and this is the closed volume that we have, and the volume of this figure, it is given by, this is 3 times triple integration of dv of v, this is equal to 3 times the volume of tetrahedron, that is OABC, and these are the coordinates that we have. And the formula for the volume of tetrahedron, we know that is equal to, it is 3 times 1 by 3 times area of triangle OAB into the height OC. So we are writing this is equal to 3 into 1 by 3 into 1 by 2 into 6 into 3 into 2. So 3 into 2 gets cancelled, and the answer we obtain, that is equal to 18, and this is the value of this integral. This is the value of this integral. Next is use the divergence theorem to evaluate v vector dot n cap ds, where v vector is given by this over the upper half of the sphere x square plus y square plus z square is equal to a square. So we are saying the surface that is given to us, it is the upper half of the sphere. Now this surface, it is open from this side. So to close this surface, we are saying we have added a surface, this portion we are saying we have added this surface S1 to this given surface. We are given the upper half of the sphere. This surface is given to us. Because this is an open surface, we have added the surface S1 to it to make it closed. So we are saying we have two portions now. One is the curved surface, this S, and then we have this lower surface, it is S dash. Now if we evaluate the value of divergence of V, the answer we will have, it is the partial derivative with respect to x, it is 2, then partial derivative with respect to y, it is z, and partial derivative with respect to z, it is 2z. So we are saying it is 2 plus 3 z. So we obtain triple integration over V. V is the volume bounded by this hole, this surface S union S dash, and the integration we have, it is 2 plus 3z into dx dy dz. Now if we use the spherical polar coordinates over here, we obtain that this integral will change to, it is triple integration. In place of 2 plus 3z, we will have 2 plus 3 r cos theta. Then in place of this, we have r square sin theta dr d theta d phi. Now the value of r, that will vary from the radius of this circle, we have, it is a. So limits for r, it is varying from 0 to a. Then we have the upper half of this sphere. So because it is upper half, so we are saying the value of theta, it will vary from 0 to pi by 2. If it is complete sphere, then it is 0 to pi, but it is upper half, so we are saying it is varying from 0 to pi by 2, and the limit for phi, it is varying from 0 to 2 pi. We are talking about this integral. We evaluate this integral. The answer we obtain, it is equal to, these calculations, these are shown over here. When you evaluate this integral, the answer you obtain, that is equal to pi a cube by 12 into 16 plus 9 times a. So we have obtained that double integral over the surface S v vector dot n cap into ds plus double integral over the surface S dash v vector dot n cap into ds, that is equal to triple integral over v divergence of v vector into dv, and this is equal to pi a cube by 12 into 16 plus 9a. Now if we evaluate this term, we are saying the surface S1, it is the circle. Now the normal vector to it, it will be minus k cap, and we have over here z is equal to 0. This is the value of n cap. So we are saying the value of v vector dot n cap, that is equal to minus z square, and we have z is equal to 0, so this value is equal to 0. So we are saying the value of this integral is equal to 0. The value of this integral is 0. So we obtain that the value of double integral over S v vector dot n cap into ds, that is equal to pi a cube by 12 into 16 plus 9a. This is equal to 16 plus 9a, and this is the required integral. This is the integral that we have to evaluate. Now next we have is verify the Gauss Divergence theorem for f vector is equal to this function is given over the upper half of the sphere x square plus y square plus z square is equal to a square. So this is the similar question as we have done in the previous case. So we are talking about, we have to verify this result. So what we are saying, again we are considering this is the upper half of the sphere. This surface we are saying it is the surface S. We have added to it another surface, we are saying this is the surface S dash. Now if we draw the normal over here, this normal, it is minus k cap. Normal to this sphere, it will be given by 2x I cap plus 2y j cap plus 2z k cap divided by 2z k cap divided by the value we will have, it is 2x square plus y square. So we will get it is 2 times a, this gets cancelled, So this is the value of n cap. Now we are talking about the value of, on the surface S dash, we have n cap is equal to minus k cap. We are writing z is equal to 0. So integration over S f vector dot n cap into ds is equal to 0. We are saying on the surface S, we have n cap is equal to 1 by a x I cap plus y j cap plus z k cap. So the value that we have obtained over here, we are saying this is the value of n cap. It is f vector dot n cap that we obtained is 1 by a into 2x square z plus y square z plus z cube. Now we have to evaluate the integral. We have x, y and z, three variables over here. So we are taking the projection. We are taking the projection on the xy plane. That will be a, this is the xy plane that we have over here. We are saying that will be a circle. So we are making the substitution over here. X is equal to a sine theta cos phi. Then we have y is equal to a sine theta sine phi, and z is equal to a cos theta. And as we are talking about the upper half of this sphere, so we are saying theta will vary from 0 to pi by 2, and the value of phi that will vary from 0 to 2 pi. The integral becomes, it is double integration. We are saying f vector dot n cap, we have substituted this value, we get it is a square sine theta cos theta into a square sine square theta cos square phi plus a square into d theta d phi. And the limits that we will have over here, the limits for theta, they are varying from 0 to pi by 2, and phi it is varying from 0 to 2 pi. Why these limits are there? Because we are talking only about the upper half of that sphere. So on integrating these terms, these calculations, these are shown over here, we are obtaining the answer as 5 by 4 pi a raised to the power 4. We obtain the answer as 5 by 4 pi a raised to the power 4. You can look at these calculations. This is integration with respect to phi, this is with respect to theta, this is with respect to theta, and this is the answer you have obtained. So the final value of the integral, it is integration over the surface S1, that is equal to the value of the integral, this surface we are saying this is S1, this is value of integral over S dash plus value of integral over S. The value of integral over S dash, it is 0. So the answer we are getting, the value of the integral over S, it is 5 by 4 pi a raised to the power 4. Now we have to verify the divergence theorem. So we are calculating the value of divergence of f vector. So the answer we obtain in this case, that is equal to the partial derivative with respect to x, then with respect to y, with respect to z, and on solving this, the value we will obtain it is 5z. And on solving this integration, we are saying it is triple integration 5z dx dy dz over the surface V of the sphere. Now using the spherical polar coordinates, we get it is 5 triple integral r cos theta r square sin theta dr d theta d phi. Limits we have it is 0 to a, then we have it is 0 to pi by 2, and then we have it is 0 to 2 pi. And on solving this